Alright, hell yeah. So we have a statics problem. So this was given to me by a student at the coffee shop, and hell yeah, we're going to go over kind of the introductory part of this. We're going to try to make a simpler problem to see what's going on, because I was just given this, you know what I mean, just all of a sudden at the coffee shop, and it's just like, dang it, you know what I mean, can I get the right answer? So this is going to be a textbook would say statics, engineering mechanics when it comes to statics. Statics means things are not moving. We have a chunk of mass, we're applying a force on it, but guess what? Like, it's not moving. And that is kind of fascinating because Newton's law of motion says if I just have a mass just floating in outer space, and I'm able to put some sort of force on it, you know, because maybe I built a little rocket ship and we got fuel coming out. This force on that mass is going to cause a change in velocity due to F equals ma. So, this change in velocity, this force is going to cause this acceleration. So that's kind of the equation. You really want to rearrange this equation and say that acceleration is this force divided by this mass. So there you go. You increase the force, you increase the change in velocity per second. So we have a change in velocity and a change in time. That is the definition of acceleration. All right, sweet. So, all right, enough intro of what the hell statics is. Statics says, well, this thing isn't changing velocity, and therefore we must have, if I can identify one force on this mass, but I observe that it's not moving, whether the velocity is constant or it just has initial velocity of 0, and a short time later its velocity is still 0. So if that is the case, there has to be an equal and opposite force holding that in place. So, hell yeah. And sometimes that, it doesn't seem like when things are on Earth and they're just like, like gravity is pushing it into the ground, or just, it's a heavy car, you just don't think about this. The idea that this is still, in the universe sense. I mean, I got an Earth. The Earth's just floating in the universe. And then at some point I have a little car on this Earth. And we're applying a force. More or less we're applying a force that way. So, you know what I mean? Why not? Like, why isn't it moving? And, why is it any different than it's just a floating chunk of mass? If I do have this force and I see that it's not moving in that direction, there must be an equal and opposite force. You know what I mean? So it's good to, I like to think of things as floating, because a free body diagram is where we're going to analyze just the mass of the car, and it's identical to have it floating in outer space. And then what we're going to do is we're going to apply a force at the center of mass towards the center of the Earth, which would just be straight down. And then we're going to apply this force with the rope. And then we're going to see that, hey, if that happens, those are the two obvious ones. Gravity is always obvious if you have something with mass. And then, forces are pretty obvious because you're just like, hell yeah, I could do a force. I could pull on something, and I know how many pounds of force I'm pulling. But if that's the case, a free body diagram is going to be, so let's do it, is going to be this car. And, so hell yeah. So we have this car, and then so from the free body diagram perspective, we can just, pretend like it's floating in outer space. And this is 100% what a free body diagram is. It just says, hey, and it's kind of like a clean slate. If you just have this thing as the only thing in the universe, and then you go ahead and apply a force, on it right there, that simulates what gravity is doing. Gravity is saying, hey, this car is made of mass. It's the equivalent of taking all that mass, putting it at the center of mass, and applying a force down. That's the equivalent of what mass is when you have an Earth underneath you. And hell yeah. And sweet. So we do have this force. And yeah, so that force is going to be the weight of the car. The weight of the car is mass times gravity. I have said that anytime I use this, lowercase g for just gravity, I'm going to write Newton's gravitational equation, which says the force of gravity is gravitational constant, the mass of, let's say, the car, mass of the Earth divided by the radius of the Earth squared. Now, it's not just the fact that it's the radius of the Earth, it's the distance. Again, this is the center of the Earth, this is the center of the car. It just doesn't matter whether this car is on top of Everest or at the beach. That difference in elevation between beach and Everest is potatoes compared to the actual radius of the Earth. So just for, in general, we can say that any experiment done on Earth, the distance from the center of the Earth to the center of that car is just going to be the radius of the Earth. These three things, don't change. Mass of the Earth ain't changing. That's a constant. And so that's going to be 9.8. You can even, 9.8, 9.81, or just who cares, it's 10. A lot of tests will just say, hey, let's do this at 10 because we can kind of simplify things a lot. Alright, hell yeah. So this is just kind of an overview of a free body diagram, and we have a force, and then we have this other force that we're pulling. And this is identical. Anytime you have a force, I'm trying to get better. It's easy for me to see that the components of this would be like, hey, it's this way and then that way. Well, sure, but it's also this way and that way. And I can choose any two sets. I can choose these two sets. I can choose these two sets to represent this force. Or I can choose this one and that one. Which, these two are probably more visually appropriate. Because, hey, right here at the car, I'm basically applying up with a force and then over with a force. Cool. But then from the free body diagram perspective, and just the Newtonian perspective, we have a mass, and we just all of a sudden put a force on it. Like, we put two forces. So why isn't it moving in that direction? Why is it not moving in this direction? Why is it not moving in that direction? Well, we're going to find out that, these were the easy ones. And even if I just had these two, check it out. Like I have, to simplify this, I have a mass and I have a force down. We're just going to call that the weight. And then I have two forces, one in this direction, and that's just going to be F of x. And then I have this, so this would be F of x, and this is just F of y. Those are the components of F. And then so I have a force, what the hell did I just do? I don't know why. I was trying to simplify this. I think I just chose... Okay, so let's redo this. So I have the mass of the car, I have a weight down, I have this force F of x to the left, and then I have a force F of y. So even if it's like this, hey, these two could balance, but I still have a net force in that direction. So this thing would have to move across the universe that way. I would have a change in velocity, every second. And so I would have an acceleration because of that force right there. Because I'm applying a force that way, this car should be moving that way. So then the question is, why isn't it? And so this is kind of like the cool thing about every statics problem, is because they have some sort of real world experiment you can do. You can go to any car and throw a rope on it and then start to put this horizontal force on it, and you're like, why isn't it moving? Newton's law says I just put a force on this car, on this mass, why isn't it accelerating in that direction? Well, it's because there must be, and even if you don't know where the hell it comes from, there just has to be. Like if the experiment by observation says you're putting a horizontal force that way, you know what I mean? And again, this does have a vertical component, but hey, this mass also has a vertical component, so we're just like, yeah, those two, might balance. So we're not worried about that. But this one, visually, there's no other force that's opposing it. But when we run this experiment, we see that the car is still stationary, it's not moving. So there has to be some force in that direction to balance this, and that's going to be the contact point with these wheels. These wheels, like molecule for molecule, here's like the rubber, and it's jagged. At the molecular level, that wheel is jagged. The surface of the road is also jagged, and so when we're pulling on it this way, those molecules are interacting in a spring-like fashion. Alright, I just said these are acting in a spring-like fashion. I would say throw that statement out, but there is something unusual about friction that even the pictures don't portray 100%. Because friction says this, like, hey, these molecules are interacting where, you know, let's say at the molecular level, we have a rough surface, and then the other surface is touching. But if this mass is very little, you know, these things won't overlap very much at all. But if this mass gets bigger, then these molecules will have more interaction, and we can apply, it'll take a bigger force to kind of have those molecules finally slide over each other. Maybe kind of instantaneously break those bonds, and then we have motion. But there's going to be a force max where these molecules will resist, and then just a little bit more force, they're going to break, and we're going to have some velocity. But in both these scenarios, the velocity is zero. If we just have a little bit of a mass, the molecular interaction is small, and so the force max required to get some velocity going is also small. And it just happens to be that the more force we put down, you know, or like, you know, the more weight or mass or however you want to say it, or just force in this direction, pushing these two surfaces together, those molecularly rough surfaces, the more force it will take. And it's proportional, you know, and it's linearly proportional. And so if I don't have any weight is zero, it won't take any force. It'll take zero force to get that thing to move across a rough surface. Yeah, so even if you could have the roughest surface in the world, but if you have something that is the lightest weight substance in the world, it's still going to take a very tiny force to move this mass over that rough surface. Alright, and with this, if we double the mass, you know, maybe this mass is twice that one, it's going to take twice the force. And so that's kind of interesting. You quadruple the mass, it's going to quadruple the force needed to get that to go. And I think that relationship is still unexplained at an atomic level. You know what I mean? Especially even with material mechanics. I mean, sure, you have molecular interaction, and is it like a post? You know what I mean? Do we have two, you know, like where these molecules are, you know, like shearing sideways, and this one goes back until they release? You know what I mean? I'm kind of fascinated. I've done an example of, you know, friction being like, well, you could have it like one being a plastic nylon piece of Velcro, and then the other being a thread with a loop at the end. And so those are your two surfaces. You move this surface this way, well, that this nylon piece of Velcro is going to lengthen out, and then it can't no longer grip that loop with thread. And so we have moved this, and in that moving, it required energy to uncurl that nylon loop, and so therefore it required force to make that. I don't know. I typically do not talk about energy, but that's a good one to show. It's going to take energy to uncoil that nylon loop, and so that's the force that's going to be required. Except the only thing different about friction is that the more force you put, so let's say this is just a force of 1. If I put a force or a weight of 2 in the downward direction, for some reason, there's this other nylon loop that hasn't gripped. But if I put twice that force, then both those loops are going to grab, that nylon Velcro. And so now it's going to take twice the force to separate those. So I think that's a fairly decent analogy. So that's the plastic nylon, and then here's the thread with the loop. And so it took 2 times the force to pull. All right, and that's the bread and butter of actually friction. I think that's a more important concept to reiterate in your head than, I don't know, but yeah, the fact that I don't think molecularly there's good explanations enough that would satisfy me. I really haven't looked in, but that would be PhD level stuff of what's happening at the molecular level. That the fact that you can just put twice the force and it requires twice the friction now. You know what I mean? That's like that. I don't know. I find that fascinating. All right, sweet. So this horizontal force has to be balanced by the friction forces at the contact surface of the rubber, where the rubber meets the road. So, but still, we have a free body diagram. The free body diagram says I'm going to chop this mass out of the experiment and then just pluck it. And I really do. I think it's very useful to say, let's just put this experiment in outer space and see if we can mimic the experiment. And so this is just floating in outer space. I put the downward force. I put these 2 components of the forces. And then I put forces on both of these wheels to balance. And so now for this experiment, this thing is not moving. And we have the same scenario going on. And cool. All right, hell yeah. So now what we're going to do is kind of play around with this concept of friction. I think we've all kind of heard that if I have a mass block and I have a friction surface, right? And I put a force on this block, that the force required to move the block is going to be some sort of proportion to the weight. So the equation would be the force required to move. I'm going to put some subscripts. So force of move is going to equal this little coefficient. This is the static coefficient of static friction. It's mu s. This is the Greek letter mu, and subscript s for static. And so we're going to multiply that by the weight. So this is the equation. The equation says this force, the number on it in newtons or pounds, is going to equal, some sort of number for a constant as a multiple of the weight. Now, just know that like wood on metal or like rubber on the road, you're going to have numbers that are less than 1. It doesn't mean that, and most materials that we're just in everyday contact with that, behave in this, that we can actually use this coefficient of static friction, will have a number less than 1. But it doesn't have to be the case. You can have a material where the second that you put any weight on them, like holy Toledo, they're like stuck together. And but the only thing that I would say with that is this subscript usually, usually or always has to be applied to this equation. So what this equation says is if I double this weight, so we're going to go 2 times this weight, this number stays the same. This is a constant. So we can do a C or a K for a constant. And so that's going to make this force, it's going to double the force, double the weight. It's going to require twice the force to move. So even if you do have a material that has a coefficient of static friction that's more than 1, I apply a little bit of weight, but man, I can't even get these things to move. If I put 10 pounds of pressure, it's like I'm going to have 100 pounds to shear it. But if that's the case with that material, it also has to follow this equation. So if I push 20 pounds of pressure, to get these to do that, it's going to require 200 pounds. So keep that in mind, and just most things have a coefficient of less than 1, but definitely does not mean that everything is less than 1. You can have coefficients of friction that are greater than 1. It's just a proportion of the force horizontal to move that across that surface. And it might not seem 100% obvious, but like obvious, it's like, well, why are we even talking about the force that's that direction? Well, because that force is, what would you call it? Parallel to that contact surface. Because obviously, if we came in with a crane and we just lifted this mass, then we're free to move it however we want. And so that's one way. You have a mass on a frictionless surface, just pick it up with a crane, and then you're just going to move it through space. There's going to be hardly any friction at slow speeds through space, or through air, whatever. So that kind of shows just like, well, yeah, when we're talking friction, usually we're trying to get something to move by applying a force that way. Now, like, hey, maybe your crane, you are trying to get something to move, but you just have a crane that's not actually strong enough to pick this darn thing up. It can only do half the job. So we're going to say it can do half the weight, and then you have a team of people that are able to rope this up and then pull the rest of it. You know what I mean? And then maybe you can get it slid across. And it's just like, does that make sense? You know what I mean? If this crane picks up half the weight, it's still on the ground, but that's going to make the people's job able to move it. It's going to make this half as hard to move. And so that's what this equation. If you reduce the weight by half, it's going to be half as hard to move. Because even in this problem, we have an upward component of this force. We have an upward component, and then we have this component that's trying to slide the car. Alright, hell yeah. And so that took a long time to get to where I actually wanted to get to pretty fast, but that was, let's guess. So let's come up with, we still need to understand this equation 100%. But so what's the simplest thing about this equation? Like, I'm just going to use US units, is that most cars weigh, I don't know, about 6,000, sometimes 5,000. 5,000 to 6,000 pounds. So let's just do 6,000 pounds. And this says we have a coefficient of static friction of 0.3. So we really want an intuitive way of understanding this. Like, what if the coefficient of static friction was 1? That means that whatever this car weighs is going to be the force. And so in this diagram, we're going to simplify it. This force is in an upward direction and an over direction. We're just going to say, hey, I'm just going to have, this is the only force that I'm going to try. I'm going to try to pull perfectly. I'm going to put a block here, and then I'm going to lay down on the ground. And then we're really just going to try to pull this, you know what I mean? And can I get it to slide across the ground? Now, I'm sorry I haven't read the problem, but these brakes are locked. And so we have, the brakes are totally locked. These things, you know what I mean? So for this, just pretend like these aren't even wheels no more. Just pretend like you welded all the hubs together as well. I don't know, yeah, it doesn't even really matter. The same thing, you could take the wheels off and then just bolt on chunks of rubber, and it wouldn't even matter. The chunks of rubber could be totally square, and the contact patch could be much bigger than, so if I have 2 of those on both sides, that contact patch could be much bigger than the actual contact patch of the rubber itself. So that's probably the second most interesting thing about static friction, is it doesn't matter if, yeah, hell yeah, because if these tires are pumped up, we have a contact patch, might be about 8 square inches, I don't know, you know what I mean, whatever. We could actually do that. I'm sorry, I'm gonna do this, because we have 4 wheels. Let's say each wheel sees 1,000 pounds. 1,500 pounds. So we got 1,500 pounds per wheel. And then we have a tire pressure of 30 pounds per square inch. And so each of these square inches is taking 30 pounds of the load. And so how many of this? Well, if this was 3,000 pounds, I would need 100 square inches. And so, but it's only 15. So I have, wait, did I do that right? 1,500 pounds per wheel? I feel like I'm messing up here. 30 pounds per square inch? Square inch. Yeah, square inch. That's where I'm getting messed up. So yeah, so if I had if it was 3,000 pounds per wheel, I would have to have a surface area of 100 square inches, which that just kind of threw me, but no, that's just 10 by 10. 10 inches by 10 inches. Now if it's 15, it's going to be half that. I need 50 inches squared. And so 7 times 7 is 49. So hell yeah. So I need a contact surface that's 7 inches by 7 inches. And so that's more what I was thinking. I was thinking a contact patch of a tire is about 8 inches. And we could just say it's... Yeah, so am I doing something wrong? I'm going to turn off the camera just to make sure I'm good on that. Alright, hell yeah, I turned the camera right back on because we really need to, find methods to not get flustered and stuff. And so the units, what I like to say is the units are the equation. So we're going to have 30 pounds per inch squared. So that's the pressure in a tire. And did I do this right? Half is 3,000, and then 1,500 pounds per wheel. So I have pounds and pounds per inches squared. What do I need? I want inches squared. And so I'm going to take pounds and divide it by pounds per inch squared. The pounds are going to cancel, inch is going to go to the upstairs. So I'm going to have 1,500 divided by 30. And so we're just going to drop a 0, so we have 150 divided by 3. I'm going to say this is, it's really good for me to do mental math. This is just 15 times 10 divided by 3. That's a really good place to go because now I can see that 15 is 5 times 3 divided by 3. And I've been trying to do more, less calculator and taking numbers. And I think it would be also, this is cool because even complicated numbers where it's just like, 196. You know what I mean? What's that going to reduce to? I'm going to divide by 2, and then I'm going to get 98, divide by 2, and then I'm going to get 45 plus 3, 45 plus 4, so that's 49. You know what I mean? And then what is this? Well, this is 7 times 7. But yeah, it's just kind of fascinating. So that was divide by 2, 7, 7. Hopefully I did that right. So 7 squared times 2 times 2. Yeah, so just taking a number and then getting it down to its primes. And some numbers, you might need to know if it's a prime of 13 or whatever other numbers. Anyway, so I can cancel this 3 with that 3, and we got 50. So we did it right. 50 inches squared. I'm just fascinated at how wide a tire is. Isn't a tire just about? Is it close to 10 inches? Because if it's close to 10 inches wide, you're going to have a contact patch that's 5 inches by 10 inches. I just was blown away that the contact patch would be 5 inches of flat spot, because typically your flat spot is where you lose all your efficiency. And if you're taking a circular wheel and constantly flat spotting it, that gets hella hot. Alright, booyah. So anyway, so we did that because let's say I pump up the tires to 60 psi. Well, this flat spot is going to halve. We're going to have a flat spot that's only 2.5 inches by 10 inches. And so that's what happens when we pump it up to 60. But in both those scenarios, we still have the same 1,500 pounds in between the rubber and the pavement. And so this equation of the force required to pull this car, whether the tires are underinflated or overinflated, the contact patch is small or big, the force required to move. The equation on that is just this constant, this number, times the weight of the car. This equation is not a function. This force move is not a function of the area of that contact patch. And I think that's very fascinating. So I'm glad I went over that, just because those are probably the two fascinating things about friction. Is the more weight you put into something, the more those molecules interact, but they do so linearly. And so, and I just find that fascinating, because not much in the universe is linear. You know what I mean? Like a magnetic attraction, or what would you call that? Static electrical attraction. It is always like the proportional to the distance squared. Yeah, just like gravity. Gravity is distance squared, proportional to the distance squared. Yeah, so it's just fascinating to see what things are linear. Alright, hell yeah. So hopefully that little tangent was good. So we need to get back to just our guesstimations. So now let's do it. So we have a car, weighs 6,000 pounds. If the coefficient of static friction was 1, I would have to pull a force of 6,000 pounds. But the coefficient of static friction for us is 0.3, so a third of this. Okay, so that's going to be 6,000 divided by 3. I don't know. I'm sorry I did that. Like that's crazy that I thought this was close to I was confusing a third. No, I did it wrong too. Yeah, so this was a wrong calculation. That's why I was just like, okay, so this is 6,000 times 0.3. This is not a third. That is absolutely not a third. This is just 0.3. So 3 times 6, I'm going to get 18. And then this is the same thing as 600 times 3. It's the same thing as 6 times 3. Do that first times 100. You know what I mean? Because this is 6 times 100. And so, hell yeah. So I'm getting used to like trying not to use your calculator, but it requires breaking these things up into a simpler way to look at this. So this is 18 with 2 extra zeros. All right, sweet. So it would require 1,800 pounds of force to pull this car. So that's the kind of the answer we're shooting for. And now let's look at the units that they're using. All right, so they're using 2 megagrams, and the M for this is mega. This is 10 to the 6. That's what M is. So let's just write that. So we got 2 times 10 to the 6 grams, and then let's just write it as a number. 123 grams. It's kind of useful to write things like this just so you can kind of visually see them. Now, how many grams are in a kilogram? Well, there's going to be 1,000 grams. And so this is the conversion ratio. Anytime you have a ratio, always stack the ratio. So we're going to go 1 kilogram, 1,000 grams, and then do it the other direction. 1,000 grams, 1 kilogram. You know what I mean? Just with this is kind of the 3 different ways to represent it. And I definitely use this as my teaching method of just like, hey, I don't think there's 4 or 5 different ways to represent, you know, a proportion or a, I think you just say these are equivalences. So from my perspective, there's 3 different ways to write equivalences, so you might as well just write all 3 and then see which one's useful to you. We're going to use this one because if I put 1,000 grams and then 1 kilogram up here, and the grams will cancel. And because this is an equivalence, it's literally like multiplying by 1. It's the same idea of if I multiply top and bottom of a fraction, like 3/4 times 2 times 2, I can multiply by any number. And what we're just doing is basically just multiplying by top and bottom by 1. And I should explain some more, because it's like we obviously didn't. We multiplied the top by 1. So we took that 3/4, we multiplied the top by 1, and we multiplied the bottom by 1,000. Yes, but the units changed. You know what I mean? So still, 1 kilogram is the same thing as 1,000 grams. So that's where we have two different numbers, but we're still saying that these are equivalences. But the thing that will change, I'm sure there's even a better way to mathematically write this instead of just like hocus pocus. The grams cancel and you're left with kilograms. But that's how I'm going to leave it. And so 3 of these zeros are going to go away, and so we have 2,000 kilograms. In America, we deal with pounds, so I'm just going to quickly convert this. But it's not too bad because basically 2 kilograms is approximately 1 pound. I'm sorry. Holy hell. So, 2 pounds is 1 kilogram. Oh, I was going to get messed up because if I see, oh yeah, how was I going to get messed up? If I have 1,000, yeah, this is interesting. Basically, in America, if you have 1,000 kilograms, this is close enough to 1 ton. It's actually a metric ton, so it's 2,200 pounds. But the English or American ton is just 2,000 pounds. But I mean, for just guesstimating, it's good to be like, hey, 1,000 kilograms is 1 ton. 1 metric ton, that's the definition of a metric ton, but just in America it's good to see that. 1 kilogram is obviously not 1 ton. 1 kilogram is just 2.2 pounds, or approximately 2 pounds. Alright, hell yeah. So let's use what I just said for this conversion. And what do I have? I have 2,000 kilograms. And so isn't that going to be 2 tons? Yeah, so we have 2 tons is the weight of this car. Yeah, so cars can be about 4,000 pounds to 6,000. So you can really have lightweight cars that are about 4,000. Most trucks are going to be 5,000 to 6,000 though. Okay, hell yeah. So that was really good even for me just to see 2 megagrams is 2,000 kilograms. And 2,000 kilograms is 2 tons. Just because the kilogram is basically a ratio of 2. 1 kilogram is 2 pounds. So sweet. And so if I have 1,000 kilograms, that's going to be, and a ton, 1 ton is 2,000 pounds. So, you have that factor of 2 kind of twice-ish. But anyway, so hell yeah. So 2,000 kilograms is going to be 2 tons. 2 tons is approximately 4,000 pounds. This is going to be metric tons, so this will be 4,400 pounds because 1 ton metric ton is 2,200 pounds. Okay, so all I wanted to get at was just like, hey, can you look at this number? And for the next problems that I do, could I take a problem a lot faster? If it said, hey, this vehicle's 4 megagrams. Okay, I'm going to be like, that's 4 times 10 to the 6. I know that grams, and so 4 times 10 to the 6 grams, I could say 4 times 10 to the 3 kilograms, and then this is just 4,000 kilograms. That's going to be 4 tons metric, very similar to about 8,000 pounds, plus 4 times 2, so that's going to be 8,800 pounds. So yes, that vehicle, 4 megagrams would be 8,800 pounds. So it's always good to use the algebra, even if it's a slow process, to get where you want to go. And then once you have a correct answer, like, hey, go back and do it again mentally and see if you could have got there a lot faster. Because it's this fear of making a mistake. And it's a good fear too, because you really don't want to make mistakes at every little hiccup because, man, they're difficult to find. Alright, but booyah. So we have our first estimate for this problem, is that this car weighs, 2 tons. Did I say that right? 2,000 kilograms, so 2 tons. And that's metric tons, so literally it weighs 4,400 pounds. So I would need a force of 4,400 pounds in that direction. If I'm pulling at a crap angle, so that's the other thing, trigonometry says that if I'm pulling at a horrible angle up and over, then, hey, you know what I mean? I'm only getting 88.6%, and I'm 50% of that is up. Now, these aren't additive. If I'm pulling up at a triangle at an angle, both these things are happening with this force. So I'm trying to, and I guess the other thing from geometry, and we'll probably have to go there in a second, is that I need this component of the force to equal 4,400 pounds. Now I think we need to just use this megagrams or units of that. And so what we're going to use is, and even with kilograms, we just converted it to pounds, where kilograms is a mass. Kilograms doesn't mean force at all. You know, I mean, you could have this car floating in outer space, and it doesn't, technically weigh anything. It does, from Newtonian physics, it does have mass, and if you're going to apply a force on it, and you want, it to move with an acceleration, well, all that mass is going to go into that equation. All right, hell yeah. So that's going to be the next thing that we do, is we're going to use Newton's law that, or which one do we do? Force is equal to mass times gravity, or do we take the force of gravity is the gravitational constant, the mass of the car, mass of the Earth divided by the radius of the Earth squared. You know what I mean? But both those are the same. This is just g. And so, hell yeah. So these two equations are the same. So we have Newton's gravitational equation is the force of gravity, which we equivocate as the weight. So we can say, hey, right here, the weight of this car is mg, is the mass of the car times gravity. And so gravity, for this one, we're going to use, because the student's going to use 9.81 meters per second squared. And this equation is synonymous with Newton's relationship of force is mass times acceleration. And since we're going to be in SI units, this is going to be 1 Newton is equal to 1 kilogram traveling at, or accelerating, changing velocity every second of 1 meter per second change in velocity every 1 second. And so that's going to be meters per second squared. So 1 meter per second squared times 1 kilogram is the definition of 1 Newton. So those two things, writing Newton's law of gravitation and looking at the units of this. And the units will fall out of this, just because we say so. This gravitational constant has all the units to balance and make this newtons, even though that this is in kilograms, this is in kilograms, and this is meters squared. So let's do that one. These are first chapter stuffs that, it's just I don't think I want to do. So I'm going to have some sort of units for this gravitation. I'm going to have kilograms, and then I'm going to have kilograms, and then I'm going to have meters squared. So I'm just going to write it as this, meters. Okay, and how do I get newtons? Well, I need a newton right there, and then I need to cancel these kilograms. So I'm just going to put a kilogram, and then I need to cancel these meters. So we're going to go meters, and that's one way to do it. You know what I mean? Hell yeah. So we've just showed that the gravitational constant will have units of newtons, meters squared. So we have newtons, meters squared per kilogram squared. Now that's not the only way to write this, because we do have this relationship that each kilogram, I could rearrange this. Anytime you have an equation, hey, you can rearrange this 3 different ways, so let's do that. Let's solve for 1 kilogram. 1 kilogram is going to be 1 meter per second squared divided by 1 Newton. You know what I mean? So, hey, every time I have a kilogram, I can put in this meters per second squared. Let's do that. So we're gonna go newtons, meters squared, and then we're going to square this. Squaring this is meters squared, seconds to the 4th, newtons squared. You know what I mean? So the second squared's downstairs, but we're squaring everything. And then we're going to have this in the basement. So the meters squared is going to be in the basement, the second to the fourth, and then the newtons squared will be upstairs. And it feels like we messed up because it's just like, well, how is this going to cancel? Because this looks like we have newtons cubed, and we have the meters go away. Newtons cubed seconds to the fourth. And it seems like we did something wrong, you know what I mean? But hey, there's a seconds to the fourth. Let's just solve for it and see if we can go, like, undo this. I'm going to bring the seconds to the fourth up there, and I'm going to get the kilograms down there. So we got meters squared, kilograms, newtons squared. Okay, now let's plug and chug. So this is newtons cubed, and then we're gonna do this: meters squared divided by kilogram newton squared. And check it out. We're going to have 1 newton on the top. We're going to have meters squared, and then per kilogram. I think we did make one error here because we should have kilograms squared. Alright, hell yeah. So let's walk through where we might have got our errors. So here's going to be newtons, meters squared, kilograms squared. I'm going to rearrange this for kilograms. So that's going to be Newton, and the meters are downstairs. Oh, I think I got this because this was meters per second squared. So we have so 1 kilogram. So kilogram is going to be newtons divided by meters, and then the second squared is upstairs. And then if I square this, kilogram squared is going to be newtons squared seconds to the fourth meters squared. And what did I say? See, I got, I messed up where the seconds were. So this was an error. And then, yep. And so this was wrong. And, cool. So all this is wrong. So if I'm putting this into this equation, we're going to have newtons, meters squared, and then this right there. So we're going to divide by newtons squared seconds to the fourth, and then meters squared goes up top. So we get newtons, meters to the fourth. And then this newton will be downstairs. So we get meters to the fourth divided by newton times seconds to the fourth. So hell yeah. So there's another way to show the gravitational constant. So the first way was, this was the gravitational constant. Here's another way to show that gravitational constant. Alright, hell yeah. And so this is really useful because, like, are we sensing a pattern? Like, this had newtons, meters, and kilograms, but it didn't have seconds. This had everything except kilograms. So I could have a gravitational constant that has, without meters. So this one was minus the seconds. This one was minus the kilograms. So let's keep going. So, and let's write our 1 newton is 1 kilogram meters per second squared. So here's our relationship. So I can say that meters, 1 meters is newton second squared divided by kilogram. And that's what I'm going to plug into here. So meters to the fourth is going to be newtons to the fourth, seconds to the 8, kilograms to the fourth. And then we're going to put that right into this equation. We're going to have newtons to the fourth, seconds to the 8th, divided by Newton, and then so we have the bummer. You know, like this equation first, if that's what I'm going to do first. So we're going to have a kilogram to the fourth there. So those 3 terms are just that, mass to the fourth. And then we have these other 2 terms, a newton and a seconds to the fourth. So 4 of these are going to cancel, so we're going to have seconds to the fourth. 1 of these is going to cancel, we're going to have newtons third. And so hopefully I did this right. I'm not going to double check, but we got newtons to the third, seconds to the fourth, kilogram to the fourth. But this goes with my teaching style of just like, you know what I mean? Like how many, there might be one way that this gets, I think gravitational constant gets done like this like all the time. Or I might be wrong on that. This one would be the most sensical because it's going to give you newtons after you cancel those masses in kilograms. Because if this is the gravitational constant, I'm going to have 2 kilograms and 2 meters. And so I need this to be the inverse and pop out in newtons on top. But I just know that the gravitational constant, they typically don't show it in this form, especially like on Wiki. I don't know why they usually show it probably in this form. Okay, so, but what's the other? So this one was without meters. And so how many terms are there? There's going to be... and it has to have newtons. Like if the gravitational constant has to spit out a newton, it has to have a newton, newton, newton. So we have a check on those. How many other terms are there with this? Well, we have a meters, a kilograms. We have a second, and that's it. You know what I mean? Those are the 3 extra terms: meters, kilograms, and seconds. You know, newtons is what we need. And so, hell yeah. But I guess it doesn't matter. We could still write the gravitational constant without newtons, because 1 newton is 1 kilogram meters per second squared. So let's just take this equation and sub this in there. So we're going to have kilogram meters second squared. That's what this n is. And then we're going to have meters squared and then kilograms squared. So this is going to be meters cubed seconds squared times kilograms. And however you could rearrange these two, kilograms times seconds squared on the bottom. But this is going to be the gravitational constant minus n. So those are the 4 different ways to write the gravitational constant. So booyah. So that was pretty useful. And that was kind of good practice for me. And that is one of those scenarios. It's just like, well, it's not part of the problem, but, you know, are you ever going to do a mental exercise like that? Probably not, just because you're just like, I'm probably going to, like, hey, we ran into our first error right there, and we had to relax and slow down and then, you know, find our way through. And that one required solving for 4 different things. It seems completely unrelated to this actual problem, but it was just a good exercise to do. Alright, hell yeah. So I almost forgot why we even did that tangent. It's because this was a mass, and we needed to figure out what its weight was. And we're going to use that gravitational equation, which is just the weight is the force of gravity, which we reduced to mg. But again, anytime I see this mg, I'm going to write Newton's law of gravitation. Gravitational constant, mass of whatever, mass of the Earth, radius of the Earth squared. And those 3 things equal g. Okay, sweet. So the weight of this car is going to be 2 megagrams times the gravity. And that's going to be either 9.8, 9.81, or just round to 10. And that's going to be meters per second squared. But we need to have a check on reality on units. So always write F equals ma, and then write the units associated with 1 newton is going to be 1 kilogram times 1 meters per second squared. And so this is in acceleration. It's typically always going to be in meters per second squared. But this is going to be different. So we said that this was 2,000 kilograms. Okay, hell yeah. So now we're good to go. And we can say kilograms times meters per second squared is going to be 1 newton. So these 2 numbers is the amount of newtons we're going to have. And since we're still in guessing mode, we're just going to take this 2,000 kilograms times 10 meters per second squared. We're just going to say g is 10 meters per second squared. And so that's going to help us really simplify, and then we don't have to, you know, get decimal numbers even though these are pretty easy to multiply. But all right, so we're going to have 20,000. So the weight is 20,000 newtons. And so for this problem, is that number is like too big. You know what I mean? So the actual answer will be, we're going to say that 1,000 newtons is 1 kilonewton. And we're going to be talking in kilonewtons. Just because we'll get, this number will become 20. The weight will be 20 kilonewtons. And let's do factor label. You know, we'll do the total slow approach. Like this is the equivalence. Let's write it two different ways. 1,000 newtons on top, 1 kilograms newtons on the bottom. Do some parentheses just showing this is their conversion ratio. And then flip them. Hell yeah. And then so this was newtons, and so we're going to multiply by this one. 1,000 newtons on the bottom, 1 kilogram on the top. Newtons will cancel. These three zeros will cancel those three zeros, and we have 20... I'm sorry, kilonewtons. This is not kilograms, this is kilonewtons. So that's a horrible error I made. So you'll just have to bear with me. So yes, 1,000 newtons is 1 kilonewton. And carabiners, you know, will be like, hey, this is rated to 12 kilonewtons. So since I made a mistake, let's talk about other ways of looking at this. Like, what's the conversion on kilonewtons? Is how I do it is do this. So I do this every time I get a carabiner. I'm going to walk myself through the process. If this says 12 kilonewtons, I'm just going to say 12,000 pounds and be like, sweet, 12,000 pounds, but I do need to divide that number by 4. And so that's going to be 3,000 pounds. So this carabiner could take 3,000 pounds. Now, there was a lot of rounding there, and I was making the assumption that 4 newtons is equal to 1 pound. And it's a pretty bad rounding. I mean, it's close-ish, not really, because it's 4.44. 4.44 newtons is 1 pound. And this might be 4.45, I kind of forget, because I think it's 4.447 newtons is 1 pound. Don't quote me on that, though. All right, hell yeah. The other thing that I like to do is 1 kilonewton is 1 Mike Tyson, and that's going to be like kind of fighting weight. It's not just even Steven 250. It's going to be like 225, and getting more accurate, thinking as a fighting weight, you're kind of getting down to the decimal places. So we got 224.8. So that's how I remember that, like 224.8 pounds is 1 kilonewton. And so we have 224.8 pounds is equal to 1,000 newtons. And you can see that if we take 1,000 divided by 224.8, we get 4.448. And that's very similar to this number of 4.44. And it might be 8. I forget if it's a 7 or an 8 in that decimal place. But 4.45 newtons to pounds. Even in this as a decimal, I just remember a bunch of 4s. 4.44, call it good enough. Hey, that's way closer than saying this was just that guesstimate of 4. Okay, sweet. So now we have some sort of like, hey, this is, and 1 kilonewton is 1 Mike Tyson. It's also how much you can actually pull. If you had a tree and a rope and you were going to pull the rope from the tree, you could probably generate about 225 pounds. You might get a little bit of leverage off of flat ground where you could pull more than your body weight. And yanking, you know what I mean, you can generate this 1 kilonewton fairly, I wouldn't say easily, but you can probably yank up to 300 pounds. Now, if you're just applying, it could be as low as 100 pounds if you're not trying very hard. But that's definitely one in my wheelhouse of trying to, like, hey, someone said kilonewtons, and so 20 of these. So even just right here, I see this as 20 people. So if this car weighs 20 kilonewtons, if I put it on a pulley, and we had some pulleys, hey, if I got 20 people lined up, on platforms all pulling down, that's kind of a bizarre thing. I would do it like get pulleys and get the pulleys back to the ground, and then have 20 people pull in a tug of war. Pulleys can redirect this tension in the rope, and there you go. We got 20 people could lift that car. So man, that's probably the most gold part of this whole thing, this whole video currently, is just being like, what's a kilonewton? Well, it's one person pulling, and so if I see something that says 20 kilonewtons, that's like the equivalent of 20 people pulling. Because for this problem, we're going to get something approximately 6 kilonewtons. Well, how much can you pull? 1. So we already have some sort of a limit on this problem, that the force, even in this direction, would have to be 6 people pulling. But if you had 6 people, you could pull a car. And I think actually, so that's where this video right now is exactly where I want it to be. Where it's just like, hey, we want to use some sort of intuition to have like a real world answer to this problem. Because even in the coffee shop, the kid's like, hey, it's a 5.47 kilonewtons. And it's like, sweet, all I see is 3 numbers that I want to match. I want to, play the algebra lottery, and then, booyah. I want to see cherry, 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 547, pat myself on the back like I did something correct, and that's good. You want to follow the algebra to get there. But at the end of the day, saying, oh, I get it, 6 people could actually pull this car. And so, hell yeah. So if I ever just am walking down the street with a rope and 6 buddies, 5 other buddies, we can be like, hell yeah, see that car? I did this physics problem. We can move that car. We can slide that car wherever we want. Hell yeah. All right, so now what we're going to do is to see if we still have to do our guesstimate, because this car weighs 20 kilonewtons. The force required to move is this coefficient of static friction times the weight. And so, booyah, we finally got the weight. And it's not 9.8. We estimated 10, so it's always good to just know where we estimated, because we can go back and trim. Sweet, so we got 0.3 times 20 kilonewtons. And so even this is just like drives me crazy. So I'm just going to say this is sweet. You know what I mean? I've never done this before, but I can move this decimal place that way and move this decimal place that way. And so this is just 6 kilonewtons. So that was visually pretty sweet. 0.3 times 20, you know what I mean? I don't know what the hell that is. And the other way to do this is just like forget how many zeros this has and how many decimal places this is out to. I mean, the whole idea with significant figures, and I'll say it in a second, but it's just taking 3 times 2. Like visually, that's what you should see here. 3 times 2 is 6. And then, go figure out how many decimal places. Well, this was going to be a 1 to this direction, and then this one is going to be a 1 the other direction. You know what I mean? So booyah. So we got 6. The other way to look at this is 3 times 10 to the negative 1. And this is multiplied by 2 times 10 to the 1. And so this as a significant, what would we call it? Significant number? Significant digits? No, sorry. I'm saying the wrong thing. This is scientific notation. And I think the thing that up to this year tripped me out is this x. You know what I mean? Because it's just like, well, is that x similar to y? You know what I mean? Is it a variable? And so, so what I typically do sometimes on scientific notation is write it as a product of 3 times 10 to the negative 1. And then this is just another product of 2 times 10 to the 1. And it really shows you, and now I need to go back to my textbooks of like, multiplication is commutative. Well, I don't know. It's either commutative or associative. I apologize for not knowing but it means that you can multiply any of these two in whatever order you want. So I can multiply, so I can easily do the 3 times 2, and then at the end of the day do 10 to the negative 1 times 10 to the 1. And so this, you know what I mean, that's going to be 1/10 times 10. So a couple different ways to look. That's just 1. Or you can say this is 10 negative 1 plus 1, and that's going to be 10 to the 0. I swear, anything like, figuring out what the difference between 10 to the negative 1 is, 10 to the 0, and 10 to the 1. That requires, 10 to the 1. Like just seeing that this is 1 is difficult to see. Seeing that this is 10 might be fairly decent, and this is 0.1. But hell yeah, I mean, multiplying 10 to the negative 1 times 10 to the 1, I don't think it's super obvious in this form. But there you go. So we have 6 times 1, and this is a value of 6. So that's kind of two different ways to multiply those numbers together. Alright, hell yeah. So this problem requires, just from our estimate, requires a 6 kilonewton force, but that has to be in this direction right here. That has to be this f of x component. And so I need to make more videos on this. But, and so I in my last one I said, hey, if you are carrying books and someone puts one book in your hand, you're like, hey, that weighs one book. And then someone stacks an identical book in your hand, it should feel like 2 books. It shouldn't feel like 1.8 books. You know what I mean? And so I kind of came up with a scenario where, hey, if you, let's just be in a different universe where if I stack 2 books, it actually feels like 1.8 books or something. And I stack 3 books, maybe it feels like 2.7 books. You know what I mean? And then I stack 3 books and so forth, or, 2.6 or something, and then we got 3.4. So you could do whatever, but that's just not the case. We're so used to being like 2 masses of similar, or 2 things of similar weight. And if I have 4 of those, that's just 4 times the thing of similar weight. And we don't bat an eye at that. But there's a universe where you could create a universe where that scenario isn't what happens. Okay, sweet. So, and then I did the idea of, and this is first chapter stuff, is if you have a ring and you have someone pulling on this ring, at this 30-degree angle, and then you're sitting here holding this ring, and you would have to kind of hold it at this angle, but you're going to hold that ring and you're going to be blindfolded. Now, you're going to feel an identical sensation blindfolded holding this ring if someone just pulls up in that direction and over in that direction those amounts, representative of the lengths of that arrow. If someone does that, you can't tell the difference. And so it's just a property of forces, and I don't know if there's, it's so innate that it's a property of vectors, that we just categorize vectors as being proportional to trigonometry, to the trigonometry that, so if I have a vector in this direction, and forces are classic, f of x and f of y, these 2 scenarios are going to be, you can't tell the difference. There is no, they're 2 different, physically different scenarios, but you can't tell the difference blindfolded. Alright, hell yeah. And so now what we're going to do is just know, and we're going to do this the harder way because we need to get on with this. So we just guesstimated that this component had to be 6 kilonewtons. Now, if I'm just applying this force, how big does this have to be? Well, we go over here, and this would have to be 6 kilonewtons. This would have to be some sort of value in kilonewtons. And then this would have to be in kilonewtons, and we can just see this hypotenuse is going to be bigger. And so we need a way to do that. And so before we go into finding angles and doing sine and cosine, or doing this and setting up a proportional a situation that's that's proportional, And in ours, we already know the angle. We're actually given this. So there's kind of two different ways to figure out a right triangle. One is the angle, and the other is, kind of knowing at least two of the sides of a right triangle. All right, but hell yeah. But we're still in guessing mode, and so what we're going to do is we're going to draw this 30-degree triangle, and we'll draw it in that direction. I think a cool way to draw a 30-degree triangle is to get your 90, draw kind of like a quarter circle, and then it's really easy to divvy up this quarter circle into 3. See how I can kind of see that as 3 equal segments? And then just start doing those types of things. One of these angles will be 30, the other will be 60. And so there you go. So there's going to be our 30-degree triangle. And 30 degrees is always bigger. It's probably like this looks just a touch bigger than, but that's got to be fairly close. 30 degrees is actually kind of substantial. I think sometimes I would be like, hey, that's 30 degrees. And nah, 30 degrees is definitely more looking like that than that. Cool. All right, so this is going to say that this dimension is 6. So, okay, we can do that. You know what I mean? So what I like to do is then we'll divvy this up into kind of segments. So this is 3 and 3, and see if that gets us anywhere. Does this length look like that length? Kind of. You know what I mean? But this looks like more than 3. Maybe this is 4. Okay, and how about this length? Does this length look like, and so again, this is 3 and 3. Does this length look like that? Well, this length is shorter. This length is definitely larger. So this number has to be bigger than 6. I know that. And so what's one way that I could actually do that? And so it's good to, I want to do it visually before I start measuring things. And so let's start to break this one up into segments. And so if this is 3, I'm going to go like that. And so each one of those is 1. And then, yeah, so let's just use that. So 1, 2, 3, 4, 5, 6, 7. I've done this method where I just try to keep that interval. 1, 2, 3, 4, 5, 6, 7. Cool. So I think this is 7.2. Hell yeah. And so we have an estimate. If this is 6 kilonewtons, this is going to be 7.2 kilonewtons. Now, I think I skipped a step, because what we said was that vectors are similar to triangles, and I just went ahead of myself. Like this was representing 6 kilonewtons, but I actually represented it as 6 line segments. Like that length of a line segment was 6. This line segment was this is one line segment, and those line segments are all the same length. And so even over here, 1, 2, 3, 4, this is going to be maybe 4.3. And so, hell yeah. And let's see how we did. You know what I mean? So I took the length of this triangle. So this length of this triangle was just 6 of these line segments that are that long. You know what I mean? And this was going to be 7.2 line segments that are that long. And this is 4.3 line segments that are that long. So even from like an engineering perspective, I have a number and I have units on that number. I'm saying that number is associated with a multiple of that length, where this is a length of 1. Cool. It just happens to be that vectors, if this is 6 kilonewtons, this length of 6 is proportional. So this is proportional to 6 kilonewtons. And if that's the case, well, and it's just the fact that forces act like this. Forces act like trigonometry. And I need better words to say that, but I think showing this example and showing how, like, blindfolded, like, you'd be wigged out the fact that, hey, two different forces feel identical. You can't tell them apart. So that means that this force can be mathematically broken up into 2 chunks, and that's also I'm glad I just said that, because these two are 2 totally different physical representations. This one is two different forces pulling on this ring. This is one force pulling on this ring. But they still are identical. What's happening at this ring is an identical scenario. And so, so don't get them confused that they are the same. I mean, they're just representing the same thing. All right, hell yeah. And so if I have the cosine of 30, that means it's going to be the adjacent over the hypotenuse. And I swear I never write this equation at all, but I need to get better at it. Where it's just going to be this 6 divided by this unknown. We don't know what that is. So that's going to be cosine of 30 is going to be the adjacent of 6 divided by the unknown. If I wanted to solve for this, hey, that hypotenuse, get that up there, this down there, is going to be 6 divided by cosine 30. Cosine 30 is 0.866. It's also, and we're dividing by a small number, a smaller number less than 1. I always show that, so we're going to get a bigger number than 6. So yeah, let's just throw this into our calculator. So we have 6 divided by cosine 30, and we get 6.9. So we overestimated. And then this component would be half of that, or we could say the sine of 30 is going to represent this opposite, what we don't know, divided by, oh, yeah. I mean, if this is the only thing I know, I need tangent. Tangent of this angle is going to be the opposite over the adjacent. The adjacent I know, tangent I know. I need to know what the opposite is. So we're going to say, so that's going to be opposite over adjacent. Adjacent is 6. So we're going to say that is 6 times tangent 30. So let's go 6 tangent 30. And we are in degrees, so this one's going to be 3.46. So yeah, so I drew my 30-degree triangle hella big. So sorry about that. But sweet, that was just a good estimate. Alright, so from our estimations, our force that we need to pull is approximately 7 kilonewtons. So we need one extra person. It only requires 6 kilonewtons, 6 people to pull in this direction, but we're pulling at a crap angle. It's going to take 7 people. Alright, now here's a question that I'm going to propose to myself. Because if we're pulling right at this bumper, we have an upward component and we have a horizontal. So we do have a component Fy up. This component's very close to this wheel. You know what I mean? So if I actually just had that component right over the wheel, it's going to reduce the weight on this wheel. And the friction on this wheel is just proportional to the weight. And then the other thing that we can guess is, let's just say the weight is centered. You know what I mean? So the weight on each wheel is going to be half of 20 kilonewtons. So we're going to say 10 kilonewtons here and 10 kilonewtons here. So now we're getting into the meat of the problem and seeing, well, the weight isn't in the center. You know what I mean? We aren't pulling, and then we're having a upward component. I'm just going to put it over this wheel just for simplicity. So I'm going to say we have 10 kilonewtons there and 10 kilonewtons there. I know that we have to pull 6. That means that we have to pull 7 kilonewtons. That was kind of our estimate. This upward component turned out to be like 3.5 kilonewtons. We could round that to 4 and be just fine. Yeah, let's do that. So let's even just round this upward component of 4 kilonewtons. And if we apply that right at this wheel, that's going to reduce this force to 6 kilonewtons. And then it's going to, and yes, it is. So it's effectively just going to reduce the weight of the car. It's not going to increase the weight over here. And so that's kind of fascinating. And now, is that true? You know what I mean? If I have a barbell at the gym that is on a rod, like a bench press bar, you got substantial weight on both of those. If I just come over here and lift this side, does this side get driven into the ground? No, I mean, this is the classic, like, massless bar. We're just going to say this bar is massless, and we got two masses on both sides. And you lifting one just like a fraction of a centimeter off the ground doesn't drive that one back in. I mean, it's just like nothing's happening on that. So there you go. So we have, so this is reducing. And didn't we say that the actual answer in the back of the book was like 5.5 or something like that? I don't have it still in my calculator, I don't think. Maybe this one. Yeah, we'll see. Yeah, I probably do have this one in my calculator. So, yep. So, yeah, you can watch that go. But I'm just going to zoom 6 it. So, yeah, that'll go, and that'll probably be like 5.47. We can kind of look at that answer, because I did save that. Nah, that's a different problem. Sorry about that. Okay, so, but hell yeah. So now we're getting closer to, we initially guessed it took 6 people. Now we're pulling at a bad angle, it took 7 people. But we're actually pulling up on this wheel, and the actual thing that's sticking it to the ground is the friction, which is a component. Is the only equation is that the force to move, which is the force of friction, which is the max force of friction. The force to move is the force of friction when it's maxed out, where mu s is equal to the weight on that wheel. And so this becomes 3. So so if we have 10 kilonewtons, it's going to require 3 kilonewtons to slide that wheel. And it's going to require 3 kilonewtons to slide that wheel because of this equation. Our constant is 0.3. But if this gets reduced to 6, I'm going to have 6 times 0.3. That's going to be 1.8 kilonewtons. Did I get that right? Yeah, so, drastically reduced. So, heck yeah. So I only need to pull 1.8 on this wheel, and then 3 on that wheel. That's going to be 4.8 kilonewtons. Let's draw our 30-degree triangle again. If this is 4.8, and we got 1, 2, 3, 4, 5, what is this? This looks like 1, 2, 3, and this looks like maybe 6. Closer to 6, and it's probably 5.8. It's probably close to 5 point whatever. And I think this answer was actually like 5.7 or maybe 5.74 or something, if I remember right. But hell yeah, so now we're just kind of, we're visually showing that, hey, this, because we're pulling up on this wheel, only requires 1.8 kilonewtons, which is 1.8 people. It requires 1.8 people to move that wheel, and then it requires 3 people to move that wheel. So, hell yeah. So now we just, instead of having 6 people pull perfectly, we only need 4.8 or about 5 people. But if we pull at that crap angle, we need like 5.5 people or almost 6 people. Alright, I think one of the trickier things about this problem for me, because this problem is very similar to like indeterminate systems. Like, check this out. I got stainless steel welding wire that I was actually able to support my entire body weight with. I actually hung it to the ceiling, and I was able to do a physics video. And it was only supposed to take 50 pounds because of the cross-sectional area. And I was just surprised I was able to hold my entire weight. Now, what happens with steel and materials is that if this is, we're just going to say 1,000 millimeters, is I can pull on it, and it can lengthen 2 millimeters. And if I do lengthen that by 2 millimeters, I have put a pressure on that cross-sectional area of 58,000 pounds, just because I know that the max stress for steel is 58,000 pounds per inch squared. And the strain on steel is 0.002. Meaning that we're going to have a change in length compared to the original length of 0.002. And that's what we have. 2 millimeters divided by 1,000 millimeters is 0.002. So these are the two properties of material mechanics that if I pull on this by 2 millimeters, it's maxed out, sure. Doesn't mean it's going to break at 2 millimeters. steel will just actually stretch, and steel can stretch up to 1/3 of its length. So if this is, I mean, it could stretch all the way up to here. It could stretch 300 millimeters before it breaks. Typically, it'll stretch 5%. 1% would be 10 millimeters, 5%. So it could stretch 2 inches. 50 millimeters for a meter long chunk of a string of steel. It doesn't matter if it's a string or actually a bar. You could stretch that at least 2 inches before it does break or just rip apart in that direction. So it's pretty substantial. But if you only pull it 2 millimeters and then let go, every molecule goes back to its original location. Okay, and then after 2 millimeters, you know, the load required to pull this thing 2 millimeters is going to be the force divided by the area. And that can only get this max of 58,000. So this is limited by the steel only being able to see 58,000 pounds per inch squared, the pressure in PSI. And this is where I actually need to get better at using like newtons per meter squared, and like what is this equivalent to, you know, and just kind of, I kind of forget, is it 400 million pascals, which is Newton meter squared, which is 400 megapascals. That's what I thought it was. Yeah, it's 400 megapascals, where, and then this, and the modulus of elasticity is 200 gigapascals. So I think I have that right, because the modulus of elasticity of this is kind of half, it's 29, but then add 1,000 and you got 29 million. So this is 58,000, modulus of elasticity is 29 million. Okay, hell yeah, so there you go. So 400 million newtons per meter squared if you like SI units. But this can only hit this pressure, and then you can't actually, it can't take any more pressure or force. And so we have this graph where, I mean, basically, the force that I'm applied is proportional to the stress, and then the change in length is proportional to the strain. And this will go up to a pressure of 58,000, and then I can't put any more pressure into that wire. And what that means is that the force on that wire is constant. Even though it's stretching, it's hella changing length, but that force is constant. So what's the analogy here? Well, we just said that we're pulling up on this wheel. Like, let's say, yeah, I mean, we're pulling up on this wheel where now this wheel wants to slide. It seems like it wants to slide first. And but the car is going to slide at the same time because the car is connected to itself. And just the fact that you put more force into this wheel than it can take. Alright, hell yeah. So this is really tripping me out. So let's make a simpler problem. So what we're going to do is we're going to have a just a rubber block. So I'm going to say this is my wheel. And we're going to have it less weight. And then this over here is going to be a block that's twice as heavy. And these blocks are connected by a massless bar. And we're going to pull with a force on these. And so and let's say if this block was alone, it would take a force to pull it of 100. Cool. And if this block was on its own, it would take a force of 200. Hell yeah. So in this scenario, we actually need a force of 300. And that's when this thing's going to slide. But as we ramp up this force is going to go to 0 to a force of 300. So let's talk about this, because at some point we're going to put a and then the other thing about this is that as we pull, let's say we pull 10 pound or 10 whatevers. We're going to pull a number of 10. You put whatever units on that you want, whether it's pounds or newtons or kilonewtons. But this is a fairly symmetric layout, where wouldn't you agree that this 10 is going to be similar to pulling 5 on this one and 5 on that one? It's going to be balanced. So keep that in mind. And then, you know what I mean? And then let's say I pull 100. Well, this one's going to pull 50. This is going to pull 50. But because this one can only see a load of 100, you know what I mean? Cool. So let's jack this up to 200. And this one sees that 100. And this one sees 100 as well. So let's go 202. So that's going to be the force that we're going to apply. This one's going to see 101. This one's going to see 101. Or does it? Because this one can only take a load of 100. That's why I did this analogy of showing you material properties, because this happens all the time. It's just like, well, this cable, or it doesn't have to. It can be any material that behaves linearly, elastically, and has a plastic range where you get to a point and it just starts to turn into taffy. Now, it doesn't mean that once it gets to here, this drops, and I think that's the impression that sometimes people get. You get to this max force, and then all of a sudden it turns into taffy, it stretches, and it seems like this force gets reduced, or it does something like that, but it doesn't. It can still withstand that same force. So in our analogy is if these two wheels are connected and I do put a force of 202, this one can only resist 100. But back to this analogy, it's still resisting that 100, even though it's hella stretching. And so even though if this block was by itself and you put 100 and 101 pounds on it, it would move. The velocity would be, we would get some velocity there. And ran out of juice. Alright, hell yeah. But in this scenario, if we put, if we think this, even Steven, it seems like this should, but that's not the case. I don't know how to say that in more words. But yes, if we put 202, this can see 100 and this will see 102. If we put 250, this will see 100, this will see 150. And again, this can take 200. So let's go up to 300. This will see 100, and this will see 200. Cool. So if we go up to 302, well, this can only take 100, and this can take 200. And that extra force has to be applied at, one of these points. And it'll probably be applied, I don't know in that case whether it'll be applied equally, but it's going to be greater, and you're going to have movement of the system. So that's what's happening. So even if one of these wheels could move with the weight on it independently in a separate problem, could move with relatively low force, and that's what we're going to see probably because this wheel is being lifted up. But actually, this is one of those problems where you have two things going on. The weight is very close to this front wheel. The center of mass of a car is very over the front wheels. There's more weight on the front wheels because the engine is heavy as. It's just a lot of steel. You just have vacant space in those portions of the car. And really, the trunk, these are just vacant spaces where it's just like, man, you got a brick of steel up in the front portion of a car. And so in that scenario, where if all the weight is right over the front portion, well then we have that scenario where there is no weight on the back wheel. And yeah, but do not forget that it doesn't matter if all the weight is on the front wheel and we pull in this horizontal direction, it's still going to take 6 kilonewtons. if the weight is evenly dispersed on both these wheels and I pull perfectly horizontal, it's going to take 6 kilonewtons. If I'm able to put all the weight on the back wheels and then pull, it's going to take 6 kilonewtons. So the thing that, so that's going to stay the same. The thing that's going to change this problem is this upward force. This upward force is going to tend to lift this wheel, and we just showed that it's not really going to do anything to that wheel. We did that barbell analogy, wherever that was. Where, yeah, you have a barbell on the ground. You go lift up this side doesn't get driven into the ground. That doesn't happen. It doesn't become lighter or heavier. And so if I pull up right here, this wheel will get lighter. I think, and you know, I still have to say I think so. You know what I mean? The equations will tell you so, but I'm just really wanting an intuitive perspective on this. Now, what this is leveraged. So if I do have this barbell on a bar, and then I have another bar attached to it out here. You know, that's the same length, and then I go lift up right here with my load. So I can have a force up, or I could be in this scenario and lift with the same force up. So, and let's say in this scenario, this force will lift this off the ground. Cool. Then I know that, yeah, there's some things here that is just like, do I know what the weight of this thing is? It's just like, hell yeah, the weight of that is 2F. And hopefully that's right. You know what I mean? I'm trying to just build my intuition. If I lift this with a force F, and this lifts off the ground just barely, right? This thing has a weight of F. In this scenario, if I lift up with this same force, and this lifts off the ground with my max force lifting, and I can just barely get this off the ground, I know this has a weight of 2F because of the leverage here. And the sum of the moments equation would show that. I think it's very useful anytime to intuit the sum of the moments equation. It is 0, and just have an understanding that it's leveraging force. So if this is my max lifting capacity, and I can have this extension that's the same length here, and then lift this, and just barely get this to get off the ground, and so that's going to be my max force. Then I'm going to undo this barbell, like unscrew it or whatever, unconnect it, and then I'm going to have this. This is the same weight on this, and you don't call them barbells, just bars. I think they just say, hey, that's a bar of steel or whatever. I don't weight lift. Anyway, I do fun stuff for my exercise. But hell yeah, so what's the weight of this? It's 2F. So when I apply a force F up, that's my max. You know what I mean? The weight on the ground is just going to get reduced by F. It's 2F, it's going to get reduced by F, and then the weight on the ground will be F. So there you go. So what I wanted to show there is the intuition on this is where if I pull directly up over the wheel, yeah, you're directly influencing the weight on that wheel. But if I'm pulling over here, I'm leveraging it. So if this is the length of the car and I'm able to weld a rod that's the same, this is the wheelbase of the car. If I'm able to weld a rod that's the length of that wheelbase out here and then pull up with this force, heck yeah, it's going to do double duty on this wheel. You know what I mean? So that upward force is going to be like a force right out of here that's 2 times that force. So it's 2 times reduction of that weight. Where again, it's not gonna drive this into the ground because there's no like mechanism. You know, if like this was underneath, like you know, somebody pinned it in a parking garage and there was a steel column that you drove under, and then I pull up on this side, you know what I mean, and this is a pivot point, well yeah, then this would drive into the ground. But as it's done right here, the weight on this wheel won't see any other component on it. And so yeah, that trips me out, but But I think that's I think that's 100% accurate. But you know what I mean. Alright, hell yeah. So I think we can begin this problem. I'm going to do a shorter, this is just the longer version, just to really intuit the process. But I do need to solve the problem, just so when I do the fast method I don't run into big hiccups. Alright, so hell yeah. So I'm just going to do a free body diagram, and I guess this is what drove me nuts, is because people wouldn't draw a separate picture, and so I'm going to drive myself nuts and not do that. So I'm just going to pretend the ground isn't there. But hell yeah, we got a good imagination. So this car is just floating in outer space. We have this, and I'm going to say this is the weight. And that weight is 2,000 times 9.81. And so if this is 1,000 times 9.81, that would be moving this decimal 1, 2, 3, and I would have 9,810. I'm going to double it, you know what I mean? So that's going to be 18,000 plus 1,600 plus 20. So I don't know how you do that mental math. That was pretty decent, but yeah. So we have a weight of 19,620. Going to go to my calculator just because... just want to double check. Sweet, and this is going to be newtons. And we're going to change this right now. We're going to go 19.62 kilonewtons. So now we're just on board to be like, hell yeah, that's the weight of the car. Our coefficient of static friction is 0.3. So obviously, even if we just did it right now times 0.3, have that double check on reality. Or 19.62, I'm going to store that as alpha W in my calculator. So this is W in my calculator times 0.3. That's going to be, so our kind of that first guess is 5.89 kilonewtons if we pulled, you know, just directly in line. Okay, sweet. But now we have to, on this, so we have this weight down. That's going to be our first arrow. We're going to have, I'm just going to say this is AY, the weight on wheel A. And then this is going to be BY. This is going to have a component this way, FX, and then we have a component in this direction, FY. And let's, so FX is going to be the force F, cosine 30. Fy is the force sine 30. Sweet. It is good, because in my my faster video, cosine 30 is going to be the square root 3 divided by 2. So we're going to have square root 3 divided by 2 times f, and this is going to be f times 1/2, or 1/2 f. So hell yeah, just other ways where you don't, because this is a decimal. This becomes 0.866. And that just means that this is 86%. And you can see that. You know, if this length, sometimes and I didn't do this in the yet, you know, if this length is 10, you can just visualize that. Well, here's half. That looks like this. This looks about the same. This is 5. This looks like about 5. And this looks like about 8, maybe 9. So there you go. So 86.6%. Cool. Alright, hell yeah. And so this force in the x direction has to, and because for this problem we're saying it's not moving. You know what I mean? Apply this force and it's not moving. But then if we apply just a little bit more force, it starts to move. But prior to that, it's still a stationary object. So we have to visualize this idea of like the car, we're going to apply a force at a certain point where it is going to move, but just prior to that, that force is still making the car is still stationary. And again, Newton's law said if we apply this force in this direction, it has to be balanced with a force. We're going to have a force there, we're going to have an AX, and we're going to have a BX. And these forces are in the right direction because they're balancing that force. Now, you know, we said we have an upward component here, so this is the only one we're not sure about. And that's good to identify. Like, hell yeah, there's going to be, this upward force isn't going to cause a leveraging two things. This upward force isn't going to make this wheel fall off. I guess the only scenario that you should visualize is at what point are you just lifting the front wheel off. If you're pulling at such a horrible angle, like if you pulled totally vertical and you had enough upward pull to lift this wheel up, one, the car's not going to slide that way, and this wheel is going to lift up. So if you have this angle, and let's say you just have a real crap angle, all you can do is just increase the force on that angle. So you can just make this bigger or smaller. There's going to be a point where, hey, this wheel lifts off the ground, but the car this component is still being resisted by the friction of that wheel. So that's the one scenario that's when I was doing this problem. It's just like, I have to think through things like that, because if I don't, I'm missing out. And they're just, it's just good to have that intuition. So those are the checks after you do this problem, just to make sure there's still weight on that wheel. All frictional problems and tipping problems kind of have that idea, because you're sliding it this way, but you might just be lifting this wheel off the ground. Who knows? And then you just have to change the properties around. If you are lifting this wheel off the ground, well, cool. Like this wheel is going and at this angle, and you have enough force to lift this car off the ground, then you're just going to have this. You're going to have a car, and let's say this is the direction of force that you can apply, and you can apply a hella force, but there's just hella friction on this wheel. Well, the other wheel is going to be up here. So now here's the car, and then here's the force that you're applying, and then the rope attached. And then here becomes your car. You still have hella friction right here, but you still want to know the force, the number on that gets this car to still slide that way. You still have a component this way of this force, and you still have a resistive component, which is due to the weight on this wheel or the normal force that the earth feels, and this would be the normal force times mu s. Cool. And sorry for calling this normal force. I usually don't like to do that. I actually hate the this idea of normal force. I just, you know what I mean. You just label it whatever you want to label it. I guess know that it's there. That's what drives me nuts about it. I don't think labeling it N and calling it a normal force has any additive properties of what it actually is, if that makes sense. Maybe there's Latin where normal means like perpendicular to, and that's kind of because if you have any ramp, your normal force is, hey, that component that is perpendicular to that surface. Damn it. And what I just said right there is the actual definition of why the friction works. The friction only is applied to this perpendicular force. So if I do have a ramp, the frictional component, like the force required to pull this thing along this frictional surface is only a function of this normal force. And so even though like a ramp problem you have gravity and stuff, but you could still have this contraption. You could have this is kind of cool to build your own contraptions that you can put in outer space. So what we have is we have a ramp, and then we have a block of mass, and then we have and let's just make another bar, and then we have a slider, so rollers. And then we have a spring pushing down on this mass. So this whole thing, this whole assembly is just floating in outer space. So we took this to outer space, and then we have a rough surface here. And then we attach a jet engine right here, and we can turn the jet engine on. And so if we turn the jet engine on, it's going to essentially have a force on this mass block that has friction. Now, we want to know what, and we can have sensors on the jet engine that we know the force being generated. And at some point, the force being generated causes this thing to move. And it's going to be a function of the what's pushing in, the spring pushing in against this surface. And yeah, so that's kind of cool. All right, hell yeah. Let's go with this one more time. So we're going to have that same scenario in outer space, but this block is going to have a jet engine on the top, like blasting it down into the surface. Same thing. Same thing as that spring. And that force is going to be normal. What I wanted to do, and that's the force required, what I wanted to do was figure out, well, what if I have this shape, where this is a triangle block of mass, and then I have a jet engine that pushes it down this direction. Well, and this is a 45-degree angle. Well, what's going to happen is that this downward force from this jet engine is going to have a component in this direction, and then it's going to have a component in this direction. And so if we do our parallelogram method, that is going to be this is the force being applied. And so let's just make these the same length. So this is going to be the force being applied. A portion of it's going that way. And these are going to be 0.707, or the square root 2 divided by 2, or 1 divided by the square root 2. 3 different ways to say 70.7%. That's going to be a 45. So these are going to be smaller than this force, but it's going to be 0.7 times that force. This is 0.7 times that force, both of those. This is the force F. And so we have a component that way and a component that way. So if we attached a string to this, and we wanted to pull it in that direction, well, the normal force, and we still have that friction surface, we still have to overcome the friction. And so let's say, what's that? The force of friction. And that's, and think of, and if you're trying to get, just ask yourself what the problem statement says. Does the problem statement say, I want it to move? Because if you want it to move, this force of friction is max. Else, if I go up to this car and just take a rope to the bumper and then pull 100 pounds, you know what I mean? What did we say? It's just, I ain't getting it to move, but I still have a Newtonian system, free body diagram. This car still is like floating in outer space. I put 100 pounds on it, so why isn't it moving in that direction? Well, there's an equal force in this direction. Now, is that equal force 6 kilonewtons, which we said that the car could, the frictional force could be up to 6? No, it's going to be perfectly balanced to be, and let's say let's do the 1 kilonewton. Sorry for switching units. I go up to this car and pull 1 kilonewtons. We just said it requires 6 kilonewtons to pull. So on, so on the wheels, you know what I mean, is there a 3 kilonewton per wheel, force that's always being resistive? No, it's only matching the 1 kilonewton. So if I'm pulling 1 kilonewton that way on these wheels, both these will see 0.5 kilonewtons. So 0.5 kilonewtons there and 0.5 kilonewtons on both those wheels. And so that's the trickiest thing, I think, about, and that'll help you when learning material mechanics. Because I did the scenario where we have a wire that's 1,000 millimeters long, and we lengthen it 2 millimeters. And I say we maxed it out. We know the pressure is 58,000, and hell yeah. So, but let's say we didn't pull it 2 millimeters. Let's say we just pulled it 1 millimeter. That means that the pressure in that is going to be a half of this, 29,000. You know what I mean? Let's say we just pulled 1/10 of a millimeter. Well, that's going to be 2,900. You know what I mean? Let's pull 1/100th of a millimeter. Well, we know that we generated 290 pounds per square inch of pressure on that surface area. We actually know the force that we're being applied by the change in length. So that's a scenario where it's just like, and that trips you up in material mechanics, where you're just like, well, I think it's easier to take a material and be like, what force is going to break that? And break just means maybe, get into the plastic zone if it's steel, or if it's glass, actually shatter it right at its limit. But usually that limit is always that max elastic limit. And so luckily for material mechanics, that always has a distinctive point for most materials. Now aluminum will do something like that. You know what I mean? So you can thank aluminum. Alright, hell yeah. So back to this scenario. So this downward force, the component downward, is the only thing that's driving the friction. And let's say the friction was a coefficient of static friction of 0.3. So I'd have 0.7 F times 0.3. And then so I would have 0.21 F. So I would have to pull against that force of 0.21 F. But also this force is going that way, 0.7 F. So the force to get this thing to move up this ramp, and up is, this scenario is the outer space scenario. But to get it to move, but it's the same thing as this having weight due to gravity. So to get this to move up the ramp, I have to pull the 0.7 F, that this has a component that way, and I have to pull against friction. So I have to pull 0.991 F. 0.7 plus 0.21. So 0.1, it's really difficult to say. 0.91 F is the force that I need to pull to actually get this little wedge to slide up that ramp. Hell yeah. So I think we're basically now fully fleshed out of like all this different scenarios. Well, I feel pretty decent. Okay, so now we want to go back to... so that was the scenario where if you lift off a wheel, and then we kind of I don't even know what the hell we talked about. I kind of just blacked out. But let's go back and solve this one from an equation-based perspective. Let's see if we can do it. Alright, hell yeah. So now I really need to focus, else I'm just never going to finish this. So we have a weight W. That's going to be that arrow down. And I think one of the strategies I can do is to... like what did we say this was? 2,000 kilograms times 9.81 meters per second squared. So 2,000 times 9.81. Like just use my calculator divided by 1,000, because this is going to be in newtons, and then we're going to have 1,000 newtons is 1 kilonewton. Sweet. So we have 19.62 kilonewtons there. And we already stored that as W in our calculator. Cool. So we're going to have this component and this component. Well, and then this student just does this. He has F sine 30. And this component's going to be F cosine 30. So we're just done with that. We're going to have a BY, an AY in the vertical direction, and then we're going to have that resistive friction BX and AX. AX to resist this force. So let's do our sum of the forces. We'll do the sum of the forces in the X direction as 0. Okay, so we have this F cosine 30. This is going to be, when we're going to set our coordinates as this is positive X, this is our Y, this is positive Y. So this is going to be in the negative direction, this one. And then the friction forces are going to be in the positive direction. So there's our first equation. The second equation is sum of the forces in the Y direction is equal to 0. And we have an upwards F sine 30. I should have done the downward forces first. That makes the most sense. The weight is going to be down, but we're going to, just pretend I put that out front. We're just going to do it opposite. So, and then we're going to have the weight. This wheel is going to be an upward force plus AY, and then we have BY plus BY. And then the weight of this is going to be a negative 19.62. Sweet. Try to put units on things. Okay, and then so this sum of the forces are going to be 0. Okay, now we can take, and this is where the student only took sum of the forces in one location. And, so let's do that. Let's take sum of the forces at A and then see what we get. Sum of the forces at A is 0. So at A, this pole is a little higher up on the bumper. So if I actually take the sum of the forces from point A, is that this component is a distance of 0.3 meters. So we have 0.3 F cosine 30. And that's going to be using the right-hand rule, the distance with our fingers, curling them in the direction of the force. The thumb is up as positive. So we have positive moment due to that one. This one is the distance, perpendicular distance to this force. The line of action is right here. Perpendicular distance is right there. Fingers go into the direction and then sweep. Let's say you put your fingers in this way. Well, we're not backhanding this force. So you need to get your fingers in the direction from the point in the direction to the force. Sweep your fingers in the direction of that force. My thumb is down. So we have a negative. That distance is 0.75 meters, units of meters on these. Times F sine 30. This the mass of the car is going to be this is the line of action of the force from point A. Here's the perpendicular distance. And we do the perpendicular distance just because we don't want to do cross products. You could say, hey, this is the distance to there. It's got two components, an I hat and a j hat, and then cross it into the weight, which only has a negative j hat. Go through all that effort, and you'll just figure out that that is going to have a negative k component. But hell yeah. So this is going to be a negative moment, and the weight is, so we have, and that's going to be 1 meter away. So we have 1 meter times 19.62 kilonewtons, and that's going to be a negative. This is going to be a positive, and we got 2.5 meters, and we have by. That's the sum of the moments is equal to 0. So we have we have 3 equations. Now what is this? This equation just has by in it. So I'm just going to kind of do that. This equation has ax, this has bx, this has ay and by. Alright, we should probably write our friction equations. So at ay, we're saying that this force ax that's needed to resist. This force I should say this frictional force ax can resist. And we talked about this. Frictional force of friction, could be 0 if there's no, if there's no force pulling on that wheel. It could be a max. And so this frictional force could be 0 to F max. And that F max is going to be mu s times the normal force. And that normal force is the weight of that wheel on that surface. And so, so our first, and then, and this force max, this frictional force max is this ax component. So I can say ax is equal, so that's going to be right here, is equal to mu s times ay. So, and I think written like this, and depending on what letters you have, I don't know. You know what I mean? Is it good just to be like, hey, this is n, you could call it na, and then this would be nb. A lot of books probably do that, now I see why. Normal force at A, normal force at B, but I just like to say this is point B, and it's got 2 components. And it could have a moment, but you can't generate a moment from, from that point. Cool, so there's an equations, and then we have bx. Bx is mu s times the weight by. So hell yeah, so now we got, 5 equations. And when we're looking at this, we're basically saying like, hey, if I solve for by, and we want to know, what we want to know is the force. Yeah, what do we want to know? We just want to know F. So F is in those 3 equations. Alright, this equation we know mu s, so we already know mu s. So we have two unknowns here. We don't know what those are, and we don't know what these are. You know what I mean? So we have four unknowns. But those are our only unknowns. Ax, ay, and bx and by. Everything else, so every equation has an ax and a bx, or an ay and a by in it. This force is what we're solving for. Okay, sweet. So if we have four equations, or I guess, I don't know, is f, because we don't know it, is that considered an equation? I'm kind of losing my mind right now. Is that why we have 5 equations? I don't think so. Like, let's say we just knew what f was, and then we wanted to solve for, and we'd have ax, bx, ay, by. We would need 4 equations to do that, and we only have 3 equations. But then these are our other 2 equations. This says, hey, if I have ax, I can turn ax into ay. So then I'll have ay and by in this equation, and then I'll have ay and by in that equation. Cool. So it seems like I only need those 2 equations. And this is where I actually, should be putting most of my time and effort. What you're going to find is that this equation, I think it's parallel to this equation. I think that's how you do that. And I'm just going to go out on a limb here, because I'm, from a matrices perspective, maybe, is that you see that, like what you would do is if you sub these in, this would just be mu s ay, and this would be mu s ax. And I don't know. I don't know the parameters that screams that these 2 equations, 1 and 2 now, are just, this is ax and ay, ax, ay, and this is, this is going to be by. So I converted these to ay and by, and this has ay and by. We have 2 equations, 2 unknowns, but you can't use these 2 equations to solve each other, I think, because their slopes are the same. I think that both equations are parallel. That's what I'm going to assume. I just don't. Why do I not want to spend the time and effort to research that? I just think I would just be there all day. I just don't, you know what I mean? So maybe tomorrow I'll hunker down and see if those 2 equations are parallel. I think it's fairly easy to do. You just solve one for, I don't know, how do you do that? Yeah, well, obviously, let's say ay is going to be equivalent to y, and then by is going to be equivalent to the variable x. And I want to get a linear equation that's y is equal to a slope x plus a y-intercept. And so this equation, I have to get this y term by itself. So I'd get all the other terms to the other side and then divide by this mu s. Well, my x term was mu s divided by mu s. So my x term has a slope of 1. And so I can see that. Now over here, I don't have that mu s on both terms. This is my y term, this is my x term. Get everything to the other side. I can already see that my slope right here is 1. So therefore, these 2 lines are parallel. And that was good. That was a challenge where I just feel like I needed to spend 3 hours just researching that. But I thought about it today. And so that was the explanation. And I think that's a darn good explanation on the fly, to be like, hey, I can now visualize that those slopes are the same. And so these 2 equations can't solve for each other because they're parallel lines. All right, hell yeah. And then this equation, I can sub it into here, and I'm still 1 unknown away. So how I did this at the coffee shop was just like, well, take another moment equation. Take the moment at point B, and then you're going to solve, you'll get something as ay. And then both of those 2 equations now can be used, And the crazy thing is I didn't sub both of those equations. I just felt that I had to sub both of those equations into f of x. So for tomorrow, I'm going to explore that. And so let's do this. So let's sum the moments at about point B. Sum of the moments about point B is 0. And we're going to have this force, 0.3 meters, F cosine 30. That's going to be a positive. We're going to have a negative. This distance is 2.5. Plus 0.5 plus 0.25. That's going to be that 0.75, and I see it's 3.25. Cool. So we have 3.25 meters, and then we have F sine 30. So we're done with that. We have AY, which is a distance of 2.5 meters. AY. That's going to be a negative. And then we have the weight of the car, which is going to be a distance of 1.5 meters, 19.62 kilonewtons. Hell yeah. So if I'm at point B, this is going to be a positive, that's going to be a positive, 2 negatives. That's what we have, 2 positives, 2 negatives. Sum of the moments is equal to 0. So this equation is equal to AY. All right, hell yeah. So this is where the student set up a matrices, and I don't know, like I can just visualize that I have an equation for AY and an equation for BY, and I could solve these, as an equation. Just BY is equal to all of that other stuff. AY is equal to all this other stuff, and then I could throw those two equations into this equation. I've already subbed these in, so this is my AY and BY. And then once I do that, the AYs and BYs goes away, and I just have F's everywhere. And so all I have to do is just solve for that force. And so one way to get the right answer was to do that with your calculator, and then just use a solver. So let's solve this one, for BY. So BY is 2.5 times BY. So I'm going to have BY is, I just got to divide all these by 2.25. And this is where I'm just going to get it into decimal form. I thought that would be a good strategy where you just don't have, you have to write less things. So this is all equal to 0, and I want to get BY by itself. So I have to get all these terms to the other side and make sure to divide by 2.5. So this one is going to be a negative 0.3. So we got negative 0.3 cosine 30 divided by 2.5. So, and I'm just going to store this as alpha A. So we have negative 0.1039. I'm just going to go to 4 decimal places, and that's going to be F. That's stored as A in my calculator. Now this one is going to be a positive 0.75 sine 30 divided by 2.5. So this is going to be plus 0.15. I'm going to store that as alpha B. That's an F term. And then I have this, which is just 1 times that, but it's going to be positive. So plus 19.62 kilonewtons, which is W. I'm going to go alpha A, that's that negative term, plus alpha B, stored as alpha C. So this equation for my BY becomes 0.0461, that's stored as CF, plus 19.62. Now I'm going to drop all the units just to make things simpler. All right, we're going to do the same thing for AY right here. AY has a negative, so we're going to get it to the other side. So now we don't change the signs of these three things, but I do need to divide by that 2.5. So AY is, and let's do this all in one go, since we're getting kind of the hang of it. There's 2 components that have F, so we're going to be 0.3 cosine 30 divided by 2.5, and that's going to be a positive. And then we have minus 3.25 sine 30 divided by 2.5. Stored as alpha d, so we're going to have negative 0.5461. This is d in my calculator, f. And then this one, we're going to have 1.5 times 19.62, alpha w times 1.5. I'm going to store that as alpha e. So we have plus 29.43. That's e. So here is my equation for ay. Here is my equation for by. And I'm going to sub them into this equation. And so this is w. So now that I simplified it, it's going to be very easy to put into my calculator as an equation as a solver. So this is equal to 0. That's the same thing as y. Y equals in my calculator, graphing calculator. And then the f term. F is going to be my variable x for my linear equation. So we're going to have negative x cosine 30 plus, and then this mu sub s, I'm going to go 0.3 stored as alpha u. So in a graphing calculator, you can't use the x is going to be your variable, and you can't use y because y is the equation. It's y is equal to x. So there's the only two variables you can't use as constants. Every other letter you can. So let's write this. It's going to be negative x cosine 30 plus mu ay. And then so I'm going to go parentheses. This is going to be alpha d x plus alpha e. And then we're going to go to the next term plus mu s by, which is parentheses alpha c x plus alpha w. And then when I graph this, hopefully plenty of places for errors. And damn it, I must have made an error somewhere. That's a bummer. So, because we're not getting the answer. Shoot. Alright, hell yeah. I haven't found my error, but I don't want to miss out on figuring out where my error is. I mean, obviously we wrote this just with chicken scratches. So, let's just go over everything. So, the force in the x, this is going to be the negative. And that's the cosine of 30. Good there. We're going to have ax and bx be in the positive direction. That's going to equal 0. Some of the forces in the y, we're going to have a negative weight, 19.62. Positive on the wheels. And then positive with this f sine 30. Cool, good to go there. Some of the moments about a. We're going to have positive 0.3 f cosine 30 minus 0.75 f sine 30 minus 119.62 kilonewtons. And then plus 2.5 by. So that's looking good. Some of the moments at b, we're still going to have that plus 3 meters f cosine 30 minus 3.25, so this is 2.5, plus 0.5 is 3, plus another 0.2, so 3.25 f sine 30, so that's going to be negative. This ay is going to be negative 2.5 ay, and then we have plus positive 1.5, that load. Solving for ay, again, we get this one, so this might have been where my mistake is. We get this one to the other side, and then we divide everything by 2. I bet you I forgot to divide... Oh, yeah, I forgot to divide everything by 2. So there you go. So I caught my error. So, you know what I mean? Just trying to do 3 steps at once. I get this term to the other side, and I got to divide this by 2.5, this by 2.5, and this by 2.5. So this w term is going to be w divided by 2.5. I'm going to store it as another variable, f. So this one's going to be 7.848, and this is going to be f in my calculator. This had to been 1.5, that weight of the car, divided by 2.5. Stored as alpha, I'll just actually store that one as alpha e, as 11.772 kilonewtons. Sweet. And so now when we graph it, we'll get the right answer. Yeah, I actually do like making mistakes because there's a place. I don't think that's the actual answer either. Bummer. So that would say that we have to pull 9 kilonewtons, and so we made so there's some other place where we made an error. Let's still kind of walk our way through it, and we'll just double check reality. So for this BY, get more time on the clock. So I don't know anyone that can do a problem without making mistakes. But the cool thing is, like, one, we kind of know what the answer should be. But we did that guesstimation, so we knew that, like, hey, it might be more than 6 people. It might be less because we're pulling up on this car. So, yeah, we're right in that 6-7 people window. I just got an answer of 9, so obviously that seems a little bit high. Yeah, so let's go. So this BY is, you know, if I was just solving for BY, I would have to get, I would have a negative. So we have negative 0.3 cosine 30 divided by 2.5. And that's alpha A. Then we'd have a negative, then this would be positive. So 0.75 sine 30 divided by 2.5. And that's what we have. And alpha A plus alpha B is going to be that alpha C. So we're check on reality there. We're going to get this to the other side. So that becomes a positive, which we have. And that's going to be alpha W divided by 2.5. And that's stored as alpha F. Did I not change my equation at all? Like, I changed these values. Yeah, no duh. So back on this equation, I didn't change it. I changed this to F. So I changed this to a letter, but in the equation, it's still a W. So there you go. So alpha F, there's the error. Yeah. I've run into that error before where you put things into your calculator as variables, and then I have graphed them, and then I've changed the variables, and then I forget that, I changed the variable's letter. So yeah, exactly the mistake we just made. So sweet. So there you go. 2 mistakes, and booyah, that's looking way better. We got 5 point whatever. So we're going to do our 0 value. Let's get out there. 5.7, 0, left bound, right bound, answer. And hell yeah. So the answer of this is force is going to be 5.79 kilonewtons. But now that has some understanding. If we just pulled this direction, we'd have to pull 6. If we pull up, so this is a really cool problem actually. Because you're just like, well, oh man, this problem's blowing my mind right now. Because I just said that we would have to pull, we didn't use 9.8, so let's do that. So 2,000 times 9.8, 9.81, divided by 1,000. So that's that weight, 19.62 times 0.3. So we would have, if we pulled directly in line, we'd have to pull 5.886 kilonewtons. Oh, this problem really is blowing my mind. But if we pull at an upward angle, which seems like a crap angle to pull the car, we're actually releasing the weight on this wheel, and we're pulling less weight. I bet you every student that does this problem has never seen that correlation. I bet you even the professors don't see that correlation. Holy hell. So this is the magic moment for me. Hopefully we're still recording. Hell yeah, we are. And we're definitely over the 2-hour mark on this one. But there you go. So to pull a car, what's the best angle? So this problem should be, if you can pull a car with said force, what angle, theta, is going to be the best angle to pull on this car if you can hook it there. And you could really do this with an actual car. And it's going to be indicative of what this mu s is. You know what I mean? So what you should do is get this equation like theta, I don't know, theta as a function of mu s. I actually need to use the restroom. Alright, hell yeah. So for this one, I think I'm going to be done. I think this video is long enough. But the one thing I'm questioning right now, And I think it's good to question stuff because you want your intuition to build. And I swear, you have equations for things. So what I said today was that if I have this barbell on the ground and I lift this side and this bar is massless, it has no effect on the weight over here. Like that weight into the floor is unchanging. And then I said if I put a lever arm over here and then lift it up, and then just lifted this one off the ground, I said still it's going to not, like the weight on this scale is not going to increase. And I just don't, I just feel like I don't know if that's true. And I think what I'm confusing is if, let's say, two people walk up to this barbell setup and they have to transport it. And we have a bar out here. Person number one, you know, me, I'm just like, well, hell yeah. I'm just going to grab right here. Hey, can you grab over here? You know what I mean? And now we're having to hoist this thing. It's like what we know from like a bridge. Let's say this is just a massless rod and we have all the mass in the middle and now we have two people. Well, hell yeah. You know what I mean? Both people are doing the same amount of work. And if I shift this mass over here, hey, this person's carrying more of it. So even just right here, if we're lifting this thing off the ground, this person's doing way more work. And so yeah, so isn't the force over here going to be more if I lift this one off the ground? So let's go through that. So I'm going to have let's say normal force at A, and this is B, and this is point C. I'm going to have a weight, we're just going to say of 10, a distance of 1 and 1. And hell yeah. And I don't even know what my lifting force is. I'm going to sum the moments at A. So sum the moments at A are 0, and we have a 1 meter times 10. That's why I don't like to use newtons and kilonewtons, because 10 kilonewtons is hella heavy. 1 newton is not even anything, but we'll go with it. So 1 meter times 10 newtons. And that's going to be a negative moment, and then we have plus F times 2. So I can just see right here that my force, well, maybe we don't see it yet. We need to solve for F, get this to the other side. We're going to have 2F is equal to 10. F is equal to 10 divided by 2. F is equal to 5. So my force is going to be 5 newtons. And so, but the weight of both of these is going to be, there's 10 newtons here, 10 newtons there. So still this person is going to, yeah, so what I said was wrong of like lifting over here doesn't affect the weight. Because over here is going to feel, you know, some of the forces in the y direction. Some of the forces in the y direction are 0. Hell yeah. And I'm glad I'm doing this because I was kind of eating my words. I was just like, hey, if I lift up at A, well, that's what I said. I said if I lift it up at A, B is not going to change weight. Now, that is true. You know, if I'm lifting directly up at A. But if I'm lifting up at a leveraged position, so we'll do both scenarios, because this is the leveraged position, and, you know, this person has to carry more weight. And that's exactly what's going to happen here. This is 5 newtons, this is 15 newtons. The whole thing weighs 10 newtons, 10 newtons. The whole thing weighs 20 newtons. So both our forces are lifting it. And if I just lift up one edge off the ground, hell yeah, some of the forces in the y, say this NA, minus 10 plus 5 is equal to 0. So I have NA minus 20 plus 5 is equal to 0. NA minus 15 newtons is equal to 0. Get that to the other side. NA is 15 newtons. Alright, sweet. But yeah, let's do the scenario where we pull up, because I'm glad I at least got that right. If we have a barbell, And I decided to pull up right here with a force that lifts it off the ground. And I'm just going to say this weighs 10 newtons, and I applied 10 newtons of force. This one's lifted off the ground. This weighs 10 newtons. Well, we can just even see from Newton, like the sum of the forces in the y, 10 minus 10, those cancel, and then the weight on the ground is going to be 10. We don't even need to use the moment equation. So sweet. So yeah, but if we lift from a leveraged position, it's like your job is easier. But that's like having, you know, a table where all the weight is over here and two people carrying it. You know what I mean? Sucks for this person, and this person is really not doing any work. Cool. But yeah, and I'm glad some of the forces in the y direction still have to balance. If I'm only putting a small force up, you know what I mean? Well, there's still, that's the only reduction, and it's not even a reduction. If both these weigh 20, and then I lift this one off the ground with 5 newtons, then this thing, there's 15. This thing feels 15 newtons over there. All right, hell yeah. So I think we thoroughly did it. We covered a lot in this one. And I think for a shorter video, and maybe for tomorrow, I'm going to go through this one and just use variables. You know what I mean? So sine of 30 is just going to be half. I'm fine with that fraction. Cosine of 30 is square root 3 divided by 2. We're going to get everything in just terms of f. And, you know, our answer will be f is equal to, you know, 3/16 square root 3 plus 2/5. You know what I mean? That's going to be our answer for f. And hell yeah, so we'll get it into a rationalized form. All right, sweet. But yeah, that'll be for tomorrow. So hell yeah, so I'm thoroughly done with this video, so thanks for joining me. And that's a video.